Hello everyone, welcome to this lecture video tutorial in Calculus 3. Enjoy learning. Hello everyone, in this lecture video tutorial we will be discussing about the integral test. After watching this whole lecture video, you will be able to understand that these tests are one of the tests that applies only to series with positive terms. We also discuss here the p-series or the hyperharmonic series, which often used in the direct comparison test or the limit comparison test as a known series known to be convergent if p is greater than 1 and divergent if p is less than or equal to 1. Solved examples or problems are clearly explained in order for the student to work on their own as they try to solve or answer problems in their purchase calculus book as I've suggested in the Google Classroom during the first meeting. These are some of the interesting ideas to look into as you watch this whole lecture video. So without further delay, let's start lesson number 4. Everyone, welcome back. This is lesson number 4 in chapter 1 of Calculus 3. So as you can see here, title is the integral test. So for our first definition, we have here the p-series or the hyperharmonic series is defined as this expression, summation of 1 over n to the p, where our index starts from 1 up to positive infinity, where p is a constant. So as you can see here, notice that this theorem here is conjoined to the first definition. This theorem is very important, or it says that this will talk about the convergence of the p-series, and as I've said in the introduction, the p-series is convergent if your constant is greater than 1 and divergent if it is less than 1 but greater than 0. So what does it mean? So let's try to explain the first definition and expansion. Let's talk about the expansion of this series, and notice notice that if you expand the summation 1 over n to the p, where n starts from 1 to infinity, this is equivalent to 1 over 2 to the 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p, and so on, 1 over n to the p plus, and so on and so forth. So in the theorem, this says that if your this is what we call the p-series. Okay, this is the p-series or hyperharmonic series. Okay, so notice that this series is convergent if your p is greater than 1. So if you look at the theorem, and divergent if your P is between 0 and 1, including 1 not but not 0. Okay, so for example sorry, example, what happened, let's for example, these are example of a P series, summation of 1 over n, where n starts from 1 to infinity. So this is an example of the P series. You can expand this as 1 plus 1/2 plus 1/3 plus 1/4 up to 1 over n. So in this case, this is the usual harmonic series. So this is harmonic series. Okay, and your P here with your P here, which is equal to 1. Okay, this is the usual harmonic series. Okay, and based on the theorem, based on the theorem, this is 1. Okay, I'm sorry, what happened, this is 1, and based on the theorem, this is divergent. Okay, why? Because our P is in here. Okay, so the harmonic series is divergent. Another example, number 2, we have summation of 1 over n cubed, where n starts from 1 to positive infinity. You can expand this as 1 over 1 cube plus 1 over 2 square, 2 cube. Okay, 1 over 2 cube, sorry, what happened, one over 2 cube plus 1 over 3 cube, and so on, 1 over n cube. This is a P series. Okay, this is a P series. This is a P series or hyper harmonic series with P is equal to 3. Okay, so this is how you are going to use the definition, and based on the theorem, this is convergent since our P is 3 which is greater than 1 based on the theorem. So that's how you are going to use the theorem and the definition. Okay, for our main topic, which is the integral test. So you are, look at the theorem, you are given a sequence of positive terms. Okay, suppose that your sequence a sub n is denoted by f of n, where f is a continuous positive valued decreasing function for all x greater than or equal to number n, where n is an integer. Then the series summation of a sub n, where small n starts from big N to positive infinity, and the integral f of x evaluated from big N up to positive infinity, both diverge or converge, as you can see here in the theorem. So if this integral converge, then the series converge. If this integral diverge, then this series also diverge. So let's have an example. So example for the integral test. So sorry, integral test. Okay, so let's have here an example. Number one, determine if the following is convergent or divergent using integral test. Letter, no, not one. Example letter A, we have summation of 5 over square root of n, where your n starts from 1 to positive infinity. Okay, so as you can see in the theorem for the integral test, it says here that you have to satisfy the hypothesis of this theorem. It says that the function, if you let your sequence to be f of n, so and we know that the sequence is a function, first is you have to show that f is continuous, positive valued and decreasing for all x, I'm sorry, for all okay, this is correct, for all x greater than or equal to n. Okay, so you have three conditions to satisfy before you can conclude the conclusion for the integral test. Okay, so continuous. So but before that, let's recall your algebra, your calculus 1. This is about continuity. Okay, continuity. So this is the first definition that you are going to remember in your calculus 1. The function f is said to be continuous at a number a if the following three conditions are satisfied. please recall this. It should be that our f of a exists. The function value at a number a is, as you can see here, it says it exists. The second condition is the limit of the function, as x approaches to a number a exists. Okay, and then the third one is the limit of the function as x approaches to a must equal f of a. So if number 1, 1i exists, 2i exists, then the 3i says that they are equal. So if these three conditions satisfies, then the function is continuous at a number a. Can extend this definition to an interval. If for all values of the interval the function is continuous, then the function is continuous at all points in the interval. That's what basically says in the definition of the continuity of a function on a given interval. So as you can see here in the definition, it must be continuous not only on a number a, but it says here it is continuous for all x greater than or equal to n. So that's basically you are going to show if the function is continuous on a given interval. The second definition that you are going to remember, let me correct, is the, no, not definition, it's the theorem in your Calculus 1. I don't know if you remember this theorem. You are given a function, that the function f be continuous on the closed interval AB, and differentiable on the open interval AB, then these are the following conclusion. If your function, if the derivative of the function is always greater than 0 for all x in the open interval AB, then the function f is increasing on the open interval AB. They have the same argument for the decreasing function. Okay, so if the derivative of the function is less than 0 for all x in the open interval AB, then the function f is decreasing on the open interval AB. So this one is what we need. Okay, this definition. Okay, this is what we need. And for the definition of the positive valued, that's very easy. This means that your your function is positive valued uh, number 3, the function f is positive valued if it will satisfy this one. Example, if you have a what do you call this one, a real line, and then your codomain is all positive. This means that this is equal to, what happened? This one. Okay, R plus. Okay, so meaning to say the values of the function is always greater than 0. Okay, so these are the 3 conditions that you are going to remember when you are using the integral test. So for our solution for our first problem, so let's have our solution. So we are going to let our an, which is 5 over square root of n, to be equal to f of n. Okay, and then we are going to show the 3 conditions. Okay, so first condition is continuity. Okay, so for I, we have here I, we have to I forgot, so it's I forgot. We have to suppose further that our x is greater than or equal to 1. Okay, our x must be greater than or equal to 1. Why? If you remember our given, the value starts from, as you can see here, this is our big N. Okay, so our x must be greater than or equal to the big N. So here you are going to let your a to be in this interval. Okay, you have to let your a to be in this interval 1 to positive infinity. Why? Just look at here. Okay, then what is f of a? What is f of a? Based on our definition, this one is definition. Oh, what happened to our there's something wrong with what I have written here because of the internet connection. So let's try to fix this one. Okay, so happened to the connection. Oh, sorry. Oh, anyway, just have to wait a little further. Okay, so this is our f of n, and here this is suppose further that our x is this one, and this is continuity. Okay, so what is our f of a? So our function is defined to this one. This is 5 over square root of a. Okay, so remember that our a is element of this interval. So what is the limit? What is the limit of the function as x approaches to a? Okay, so this is limit of 5 over square root of n as our this is not so we replace it by, okay, we replace this one by x. So replace that one by x. Sorry, oh, what happened again? This is x as x approaches to a, and this is equal to 5 over square root of a. Okay, our third condition clearly says that the limit of f of x as x approaches to a, is this equal to f of a? Of course, this is 5 over square root of a. This one is 5 over square root of a. So therefore, they are equal. So the conclusion is thus the function f of n, which is equal to 5 over square root of n, is continuous. For all n greater than equal to 1. Okay. The second condition is for the positive valued. Okay, letter B, positive valued, positive valued. Notice that for all n greater than or equal to 1, f of n, which is equal to 5 over square root of n, is always greater than or equal to 0. So when n is equal to 1, we have 5 over and so on. 5 over square root of 1, this is always positive. This implies that the function f is positive value. Okay, so we are done with the second condition. The third is about decreasing. Okay, so is the function decreasing? So first is you have to get the derivative, and if it is always less than 0 in this interval, in this condition, then the function is decreasing. So notice that we have here f of n. F of n is 5 over square root of n. If you simplify this is equal to 5 n to the 1/2, negative 1/2. And if you get the derivative with respect to n, this is negative 5 over 2, n to the negative 1/2 minus 1 is negative 3/2. Or if you are going to simplify this, sorry, you have to wait. This is negative 5 over 2 times the square root the square root of n cubed. Okay, and this is always less than 0 for all n greater than equal to 1. Since if your n is 1, we have this is always positive. So this is always positive, but positive multiplied by a negative number is negative. So this is always less than 0. Okay, so therefore, okay, what happened? So this implies that the function f is decreasing. Okay, decreasing for all n, for all n greater than equal to 1. So let me erase that one. Okay, oops, decreasing for all n greater than or equal to 1. So therefore, we can now use the theorem. Okay, we have the integral of f of x dx n to positive infinity. So substitute, your n is 1, your f of x is 5 over square root of x dx. Why? Because our x here is, since we use the variable x, so we replace our definition to be in terms of x. So notice, if you recall your calculus 2, so this is we talk about this as calculus 2 in the topic improper integrals. This is equivalent to the limit of the integral 1 to b, your b approaches to positive infinity, and simplify this 5, let's sorry, this is x to the negative 1 half dx. Okay, so further simplify, limit of 5, this is this is 5 plus 1, we have 1 half over 1 half. B approaches to positive infinity, evaluated from 1 to b. Okay, this is, okay, simplify again, this is 10 x to the 1 half, where b approaches to positive infinity, 1 to b. So sorry, we have 10 b to the 1 half minus 10 minus 10, as your b approaches to positive infinity. Okay, so what is the limit? Notice this is limit of 10 to the b to the 1 half minus the limit of 10. The limit of a constant is constant. This is constant, but this one, this is 10, but this one is positive infinity. Why? Because as your b increases, the value of b to the 1 half also increase. Okay, so the answer, this is positive infinity. Okay, so meaning to say, this the series. Okay, therefore let's try to u, therefore accordingly, sorry, accordingly this series, let's try to use another word. Let's try to erase this one. Since we use the word therefore before. Accordingly, the series 5 over square root of n, and your n starts from 1 to possibly is divergent. Okay? Based on the theorem, since the integral is also divergent. That's problem number 1. Okay, so notice also, before I will put the end of solution here, okay, notice also that if sorry, if you will use the idea of p series, we have noticed that this is equivalent to summation of 5. This is your 5 can be put outside 1 over n to the 1 half. N starts from 1 to positive infinity. So we have here a p series. Okay, this is a p series with p which is equal to 1 half, and it says that this is divergent. Okay, so if you will use the idea of the integral test, you will see that the idea of the p series and the integral test differs much, as long as you can see how to use the definition of the p series, and if you look at the problem, then if you will notice that it will satisfy the definition of the p series, and you can use it. But if not, if you will use integral test, then if you have the same result, then as you can see, there will be no problem. Okay, so in this solution, you can say that if you will use the idea of the this one, the idea of the p series, then you will have a short answer. But if you will use the integral test, then you have a very long solution. Okay, but notice that not all problems or exercises you can deduce the problem into a p series. So for example, this one. So let's have another example. Letter B. Let's try this example. Okay, let's try this example. What happened? Okay, Hmm. Let's try this example. No, let's wait. Letter B. Summation of n e to the negative n, where your n starts from 1 to positive infinity. So if you will try to use the idea of what do you call this one, the p series, then as you have noticed, it will not work. But why? Because if you recall, okay, recall uh, your the definition of the p series. This is 1 over n to the p, where your n starts from 1 to positive infinity. Okay, and notice if you will force to use the idea of the p series, then notice that this is equal to that one, no? N over e to the n. N starts from 1 to positive infinity. So there is an extra n here. Okay, there is an extra n, and as you have noticed here, there's no other expression involved in the p series. However, if only that the given is something like this, if you change the given to this one, summation of e to the negative n, or n starts from 1 to positive infinity, then you can use the p series definition. Why? Because you can simplify this given as summation of 1 over e to the n, where your n, sorry, can I really, no, you cannot use again, because notice that our p here is fixed, but our p here is not fixed. It changes as n changes. Now you cannot use, no, you cannot use here again. Here you cannot use, you cannot use the idea of p series. Okay, for this example, we cannot again use the idea of the p series. Okay, so therefore we are forced to solve this what do you call this one, this problem using the integral test, since we did not discuss the idea of the topic called the direct comparison or limit comparison or the root test or the ratio test. We did not discuss that. Okay, so maybe later, if we remember this problem, we try to solve this given using other tests. Okay, so let's have a solution. Let's have a color black. Okay, so first let's try to show the continuity. Okay, so our n starts from 1, so we have let a sub n to be our f of n. Okay, then suppose further that our x is greater than or equal to 1, or this is our small n. Okay, This is our small n. Okay, so for continuity, we have to let a to be in this interval 1 to sorry can we look again the definition? What did I write? Above x is greater than or equal to 1, but in the definition, so let me, okay, we have this one. Okay, so let's go back to our solution. To positive infinity. Okay, so what is f of a? As you can see here, we have a e to the negative a. Second condition for continuity, we have f of x as x approaches to a. This is limit of, so replaced by x, we have x over, we can write this one as e, okay. We have x e to the negative x approaches to positive a. So as you can see here, we have a e to the negative a. Third one, we have limit of f of x. Is this equal to what happened? Okay, let's wait. Okay, here as x approaches to a, and then this is f of a. Are they equal? This is a e to the negative a. We have e to the, we have a e to the negative a, and they are equal for all a greater than or equal to 1. Okay, so is this positive valued? Positive valued. Notice that since our f of n is equal to n e to the negative n, so simplify this, e to the n, this is always greater than 0 for all n greater than 1. Okay, so what happened? F is positive value. Okay, letter C, decreasing. We have get the derivative. We have let f of x to be x e to the negative x, then get the derivative. f prime of x is equal to, use product rule, x we have derivative of e to the negative x is a negative of, okay, fixed derivative of e to the x is negative of e to the negative x plus fixed e to the x derivative of x is 1. So simplify, this is negative x e to the negative x plus e to the negative x. Okay, so let's further simplify this, the right hand side, if it's clear that this one is positive. So can we write this one as e to the negative x minus x e to the negative x, then write this one as, okay, at 1, and then so since we have a negative exponent, get the LCD 1 minus x. Okay, so what happened here is that, is this greater than or equal to 0 for all x greater than? Is there something wrong? Is this greater than or equal to 0 for all x greater than or equal to 1? So let's see. If x is 1, we have 0, and 0 is not greater than 0, but other than those values, this is clearly no. No, we have a wrong definition here. It should be less than 0. Okay, it should be less than 0. Okay, so the problem here is when x is equal to 1. Other than that, this is always negative. Okay, it's always negative other than 1. So okay, so if you look at your definition, this must be, I recall now, this must be greater than 1. Okay, this must be greater than 1. We should not include 1 here. Okay, this is greater than 1. Okay, why? Because if you look at the definition, so let's recall again the definition. So let's wait for the what do you call this one, the up to respond. Look at the definition. I think I have to correct myself. I have to correct myself before, since if you look at the definition, it says here that it must be on this interval, and decreasing, the conclusion is it must be for all x in the closed interval, and the conclusion is decreasing on this interval. Okay, so let me by the way, you can change this to, if this is positive infinity, then that's no problem. Okay, that's not a problem. Let's recall decreasing. So this one, let me correct myself that this is, conclusion here must be no, sorry, the conclusion here must be greater than 1. Okay, the condition must be greater than, okay, because this says that this is the interval 1 to positive infinity, open interval, but the conclusion must be on the open interval. It includes 1. Okay, so I correct myself in example number 1. So I guess the right term here is it must be greater than 1, since if you substitute 1.1, 1.2, 3, 4, and so on, this is always negative. So the conclusion here, this implies, let's wait for the up to, this implies, okay, that the function is decreasing for all n greater than or equal to 1. Okay. So n, or this is x. Okay, so you can replace this 1 by x. So now we can apply the, oh, what happened? Can apply the, okay, star x. So therefore we can apply the integral test. Okay, so therefore this is the integral of f of x dx, and evaluated from n to positive infinity. So substitute, we have 1, and this is n e to the negative n, d, sorry, so I forgot, so we use x here, so this must be x, sorry. So I guess the sum up, so this must be x e to the negative x, okay, dx. So I also want to correct myself here. Where are you? So I'm okay, so I am correct in this example since I use variable x. Okay, sorry for that. So what happened? Okay, this is okay. So this is improper integral. We can use the definition of the improper integral, 1 to the b approaches to positive infinity, x times e to the negative x dx. So from here you will use the previous topic. You can use integration by parts. Use integration, IBP, integration by parts. So what is our let u here to be x, and our dv is e to the negative x dx. So du is dx. We have integral of dv e to negative x dx. Okay. But this is equal to, so again, please recall your calculus 2. So this implies that we have the limit of uv minus the integral of v du, integral of v du, or du is dx. V approaches to positive infinity, 1 to b. So we have e to the negative x, positive, again integral, we have negative, this will become negative. Negative times negative, we have positive, then you have to let u sub 1 to be negative x, and then just recall your calculus 1. This is e to the negative x evaluated from 1 to b. B approaches to positive infinity. So we have here limit of negative x, substitute, okay, substitute b over e to the b minus 1 over e to the b, okay, minus, so when this is 1, we have negative 1 over e minus 1 over e. E approaches to positive infinity. So what happened here? So this will become 0, because as b increases, this becomes 0, this will become 0. This is much bigger than the numerator. So what is being left here is positive 2 over e, okay, this is positive 2 over e, okay. So this is our final answer, okay. So accordingly we have summation of negative time n times e to the negative n, where n starts from 1 to positive infinity. This is 2 over, okay, and we are done. Okay, the series is divergent because the integral of the function f of x evaluated from 1 to infinity is convergent. Okay, that's for our second example. Okay, so for your assignment. So here, do you want another example? Let's have another example. Okay, another example. Okay, for this problem, this example, 1 up to positive infinity, you will notice here that the continuity part, the positive value part are very easy to comply. However, if when we talk about decreasing, okay, so when we talk about decreasing, so from here the continuity example, so we are done, correct, positive valued, correct. Okay, what will happen if one of the hypotheses is not satisfied? For example, in this example, in this given series, the decreasing part is not satisfied for this example. Why? Because if you take the example, or en is 5 to the n over or to the n plus 3, this is our f of n. Okay, but the derivative, so replace, I'm sorry, so what happened, just wait patiently. If the derivative of our function f of x is not less than 0, okay, so 5 to the x over 4 to the x plus 3. So what is the derivative of this function? So remember that this is quotient rule. So we have 4x plus 3 square. Copy the denominator, then derivative of the numerator, which is 5 to the x ln 5. Okay, 5 to the x times ln 5 minus, copy the numerator, then derivative of the denominator, which is 4 to the x times ln 4 plus 0. Okay, so simplify. So what you will get here is you have a common, okay, your common value in the numerator is 5 to the x. Okay, to the x. Then what will remain is ln 5, no, 4 to the x ln 5 minus 4 to the x ln 4 plus 3 is the derivative of this function clear enough that this is less than 0 or greater than 0? Can we easily show that this function is less than 0? Okay, so is this less than 0 for all equal here, for all x greater than 1? So I doubt. The answer is no. Okay, so therefore the hypothesis, we cannot, therefore the hypothesis of the integral test is not satisfied. Okay, therefore what happened? Okay, therefore the hypothesis of the integral test is not satisfied. Okay, accordingly we cannot use the integral test. Okay, so for this example, this one, we cannot use the integral test, but maybe, as you can see here, this is something like in the next topic about limit comparison and direct comparison test. Maybe we can use that idea to show if this series is convergent or divergent. Okay, so that's all. So for your assignment, here determine if the following series is convergent, or divergent using integral test. Number 1, summation of n cubed e to the negative n, and your n starts from 3 to positive infinity. Number 2, we have summation of tangent inverse of n squared plus 1, your n starts from 1 to positive infinity. And then number 3, we have summation of 1 over n times ln of n raised to the power 3, where n starts from 2 positive infinity. Okay, The last one, number 4. For what values or value of p, the series summation of 1 over n times ln n times ln of ln n raised to the power of p and starts from 3 to positive infinity is convergent. Okay, so that's all for this lecture. If you have some question, you can ask by typing a comment below. If you want to have a video for a certain problem that you don't understand, you can comment in the description below. Okay, and don't forget to click the subscribe and the bell button for some updates and notifications. Thank you, everyone. Sorry, I have to insert these reminders to everyone that what I've done in this lecture is that on how to know, for me as a lecturer, how to know if the function is continuous or decreasing or positive valued. So what I did is that there is a cheat for that. What I did is I graphed the series, the function. I graphed the function into an online graphing calculator like Desmos, as you have noticed here. I graphed the function and I observe if the function is decreasing or continuous or a positive value by just looking at the graph. So since you are in your home, this is not a face-to-face lecture, or in an exam there is no face-to-face exam. You can cheat yourself by graphing the function first and then observe if the function is decreasing or not, or continuous or not. So for example, this if you recall your first recall your first example. I'm sorry, you have to recall your first example, like the summation of 5 over square root of n. That one. So if you graph that function 5 over square root of n replaced by x, okay, notice that as you can see here, your n is 1, so we have a point. As you have noticed, the function is decreasing. You look at the graph, the function is decreasing as n approaches to infinity, and there's no hole, meaning this is continuous, and this is also a positive value because the graph is above the positive x-axis. So that's the cheat for this what do you call this one, to solve the problem. I have to put a recall here. Number 1 example is summation of 5 over square root of n. N starts from 1 to positive infinity. That's basically what I did. For number 2 problem, this is, or letter B, This is summation of e to the n times e to the negative n starts from 1 to positive infinity. So if you look at again the graph for that function, so example, we have replace n by x since the Desmos does not accept the variable n. E exponent is exp raised to the power of negative x. Okay, so as you can see here in the black graph, the function is decreasing, and notice it starts from n is equal to 1. That is why the index starts from 1. Okay, so mean to say, starting from 1, it decreases the value, but again it is positive valued because it is above the x-axis, and as you have noticed, the function is continuous. There is no hole in the graph. Okay, so that's for the third the second example. For the third example, we have here summation of summation of 5 to the n over 4 to the n plus 3, n starts from 1 to positive infinity. So replace your n by x in this Desmos. So we have example 5 to the x divided by 4 to the x plus 3 Okay, so enter the red one. Notice in the red one, color red, the as n approaches to positive infinity, so notice here, the value of the function increases. Okay, so this is the reason why I write in the solution that for me the function is obvious to be continuous and positive valued because it is above because it is above the x-axis, but the function is not decreasing, as you can see here. Okay, so that's the reason why I did not write the continuity part, the positive valued part. Okay, so for your assignment, you can do the same by observing the graph first, and then you can perhaps say that the decreasing part you will solve first, and then conclude or that the function is decreasing or not decreasing, and then if it is not decreasing, then you can say that you cannot use the integral test. Okay, so just try to graph this one first for me, but if in the face-to-face you cannot do that. Okay, so all you have to do is to follow the what they call this one, the algebraic part of solving the problem by showing the definition, if it fits the definition, and then that's basically you will do if in face-to-face exam. But since you are at home, then of course you can cheat. I'm not encouraging you to cheat, but I'm telling you how to know if you can use how to use the integral test. Okay, that's all. I hope this little reminders remind you on how to use the integral test. Thank you so much.